So hi everyone, my name is Nick Diana. I'm going to be presenting this instructor dashboard we built to analyze introductory programming data. So why do we do this? Our big question was, can we use low-level log data from an introductory programming environment to help us choose which students to help? So spoiler alert, we were able to do this. This is the dashboard that we built that integrates our predictive models. So now that you've seen how this story ends, let's go back to the beginning. So the talk is divided roughly into three sections. Each section corresponds to one of our main results. So the first thing that we had to do was demonstrate that we're able to use these low-level log data to predict learning outcomes. So the data we use comes from an introductory programming environment called Alice. This is Alice 2. They've since upgraded to Alice 3, so it's slightly more slick looking. The data were originally collected by Linda Werner, and we're going to do a classroom replay to test our method. But Alice was not originally intended to teach introductory programming. Teachers got a hold of it. And now, all over the country, we have a large number of teachers using this to teach programming and the opportunity to collect a large amount of data. The problem is that there's no practical use for this kind of data. So one potential use case is helping instructors make more informed decisions about who they help. So let's say we have 10 students in an introductory programming class. And let's say that the green students are the students who are going to end up with good final grades at the end of the course. And the red students are students who are going to end up with poor final grades. So without any feedback from the software, it's difficult to distinguish between these students and figure out which students you need to help. But what if you, in some cases, are going to help a student at random, right? And this student might be a good student who doesn't need to be helped. And this comes at an opportunity cost because you're not helping a student who might need help a lot. So what we do is say, what if we had a crystal ball that we could use to look into the future and kind of get an idea of which students are going to need help and which students aren't going to need help? So of course, this is our method. This is our predictive model. So like I mentioned before, Alice was not designed for this kind of analysis. So the first thing we have to do is convert the log data from Alice into a more amenable format. So the log file looks kind of something like this. There are several lines which correspond to student steps. We take those student steps and build representations of the program, which we call code states. So these are snapshots of the student's program at each step. The code states are cumulative, so code state 2 incorporates the steps from 1 and 2. So in practice, it looks like converting this mess into data that looks something like this. So they're kind of objects of data. So each student has a sequence of these code states, and the last code state then corresponds to the program that they end up turning in. So once we have these code states, we're able to use them in conjunction with grade data to generate our predictive model. So the process for doing this looks something like this. We divide the student data into training and test sets. In the training sets, we extract the last states. These are the final programs of the students, and combine that with the grades to train our predictive model. On the testing side, we're interested in how our model performs over time. So for example, it would be awesome if we were able to predict grades in the first minute of the class. And conversely, it would be pretty much useless for this case if we weren't able to predict grades until the last minute, because we'll have them eventually anyway. So what we do is we break apart the class period into 30 one-minute chunks. It's a 30-minute class. And then within each one of those time bins, we select the last state in that bin for each student in the test set. We throw that into our predictive model to get the predicted grades for the students. And then we can compare those predicted grades with the actual grades, which we have because this is replay data, to get the RMSE for that bin. So we did this and we plotted it. So there's 4 lines here. The black line represents the total score. This is the final grade. And then there are these 3 dashed lines, which represent 3 subtasks that get aggregated into the final grade. So there's some interesting characteristics in these curves. First of all, you can see this green line. This is the 3rd task. And we can kind of see these little plateaus that we think correspond to students working on different tasks. So over time, the model becomes more adept at predicting the 3rd task as more students come online to doing that 3rd task. The other interesting thing we see here is that this kind of orange-ish line in the middle has it's the worst model. So this corresponds to the 2nd task, which if you look at the original Werner paper, they say the 2nd task is the hardest task for students to do because it requires more abstraction. So the data is our models are starting to reflect the actual tasks that students are doing. So we've demonstrated that we're able to predict learning outcomes with some degree of accuracy from low-level log data. And the next thing we're going to do is return to our big question, which is, can we use these predictive models to help us choose which students to help? So to do this, we needed a metric for evaluating how well we're succeeding at this goal. So we developed this metric we call the help index. It's a simple ratio between so essentially what our model is asking is, out of all the students in the class, which student is going to end up with the lowest final grade? And help that student, right? We want to help that student, whoever is going to end up with the lowest grade. So what this ratio allows us to do is test how good we are at guessing which student to help without knowing their final grade. So we take the lowest true score at time t and subtract it from the lowest predicted score. We take the absolute value of that, subtract it from the total number of points possible, and then divide it by the total number of points possible. So for example, if the lowest actual score that a student is going to get is 0, and we predict that the lowest score that a student is going to get is 0, then our model is doing a pretty good job. We get a perfect score of 1. But if we predict that the lowest score is 10, then we get a lower help index score. So because we're using previously collected data to test our model, we have to make some assumptions about instructor behavior. So these assumptions are, they reduce very complex variables into very simple terms, but they're more meant as a rough approximation of behavior rather than the truth of what actually happens in a classroom. So first of all, we assume that the instructor will always help the student that our model suggests that they help. We will assume that the instructor spends 5 minutes helping each student that they choose to help. And we assume that each student that's helped is excluded from further help, which keeps our model from trying to help the same student over and over again. So here's our result. This black line at the top is the help index. And we can see straight away that we do a pretty good job of guessing which student is going to be the lowest performing student. So something that's interesting about this and somewhat surprising is that help index actually gets lower over time. And we think that has something to do with how the lowest true score changes over time. So as students are helped, the lowest true score slowly rises. And we think that our model might be better at distinguishing a student with 0 points from a student with some low number of points. So it's better at distinguishing a 0 from a 1 than it is from a 1 from a 2. That's just one of our hypotheses. Okay, so now we've demonstrated we're able to predict learning outcomes, and we're able to use those predictions to to help instructors choose which students to help better. So now we're going to move to a different kind of question that's somewhat related, which is, can we increase the number of students that are helped using these kinds of methods? So we're going to do this by matching students to peer tutors based on the similarity of their code. So just like how we needed a metric to assess how well we choose which students to help, we needed a metric to test how many of those students we're able to help as well. So we call this the efficiency index, and it's another simple ratio. So of the total number of low-performing students, these are students we operationally define as needing help, how many of those students are being helped or have been helped at any given time point? So like I mentioned, we're going to increase the efficiency index by essentially increasing the number of pseudo-instructors in the form of peer tutors. So the process of matching these students to peer tutors looks like this. So you'll remember this flow chart from earlier, and you may have noticed how it goes on at the bottom. So down here, what we do first, once we have the predicted grades for the test set, is divide the students into two pools, right? So we take the bottom quartile of students and we remove the students who are being helped or have already been helped. And what we're left with is a pool of students who still need to be helped. These are low-performing students who've not yet been helped, and we call that aptly the help pool. So on the other side, we take the top quartile and we remove students who are already helping another peer student. And that gives us our tutor pool. So the process of matching a student to help looks like this. If the instructor is available, then we just match a student straight away to the instructor. The instructor is the expert, so they don't need to be matched on any kind of similarity metric. If the instructor is unavailable, if the instructor is already helping another student, then we search the tutor pool for a similar peer tutor. And we define similarity by a closest common ancestor. So how we do that is we made this interaction network. So it doesn't come across very well on the screen, but it's not important. It's just very complex. So we're going to drill down at a kind of cartoon version of that. So let's say this is a subtree in our interaction network. And let's say that node C here, which these represent code states, and the edges represent state transitions. So let's say student C needs help, and D and E are potential tutors. What we would do is say, well, E and C share a common ancestor, B, that's closer than D and C, which is A. So we'd match C to E. So that's all we mean by closest common ancestor. And so the reason why we do this matching this way is because even if E and C are very different, if they have different program states currently, which they probably do, right? Because one student's doing very well and one student's doing very poorly. What we're saying is that they still share some common ground at some point in the past. So when C gets matched to E, it doesn't this student doesn't have to go all the way back to the beginning. They don't have to start from square one. They just have to go back at most to node B, and then they can get on the right track from there. So we reran our model with peer tutoring incorporated, and what we found was that we were able to increase the percentage of low-performing students helped from 50% to 79%. So that's pretty good. But there's some other interesting contributions of peer tutors that are evident in this graph. So you'll remember that instructors help students one at a time for 5 minutes each. And you can see that in this blue dash curve. That's the percentage of students helped by the instructor. You can see these steps, right, as the instructor becomes available. But those steps are not quite as evident in this orange helped by tutors curve. And that's because new tutors are coming online, becoming available to help every minute. So incorporating peer tutoring into a model like this not only increases the number of students that are able to be helped, but it also increases the efficiency of the help, which we see in this black line. It's much less, there's still a little bit of steppage, but much smoother than the blue line that we had previously. So the last thing I'm going to go over is the dashboard that we built. If you'd like, it's live at this URL at the bottom. You can play around with it. But just very quickly, up at the top, we have a timeline, which allows us to scroll through the time in the class. Remember, this is a classroom replay, so we already have the data, so we're able to play it back and inspect it at any time point we'd like. Below that, we have a class summary. This is, we use our predictive models to guess how many students are working on each task. Below that, we have another application. So each one of these circles represents a different student in the class, and the color represents their predicted grade. So you can see these colors change. There's some icons that correspond to different statuses, like the lowest performing student. I don't think you can see it here, but we have a little graduation cap that comes up if the student might make a good peer tutor. So if you select one of these students, you can see some more information about them. This doesn't show up here, but these are previous code states. And then you can look at their current code state as well as some stats. So finally, I'm going to talk about some future work that we're currently working on. So we have two lines of work. The first one is we're looking at ways to improve the accuracy and the interpretability of our model. So this model was fairly accurate for this kind of work, but it kind of lacks in interpretability. So we're working on that. And we're working on improving the efficiency of help. And one of the ways that we're going to do that is by grouping students who are struggling in a similar way together, and then matching those groups of students to tutors. So thank you very much, and I'll take any questions. Yeah?
Can you just clarify for me again what the lift is from a peer tutor? So you identify a peer tutor as had a similar parse tree in the past. You assign the peer tutor to help the individual. And how did you determine how much value that help was worth?
Right. So we did not determine the value of the help. That's something that would be very hard to estimate after the fact with replay data. So what this graph, if I can go back to it, what the increase showed, I think I passed it. This is the number of students helped, not the value of help. So as each student is helped, that student is removed from the help pool.
So you could match a tutor, and the tutor could, let's say in a real world situation, say, oh, here, I think you need to do this. And then the other student can say, but I don't understand. And the tutor's like, oh, I guess I don't get it either, and now they're both worse off. Yes, that's a potential use case. Yeah, so what we'll need is a real-world implementation to test that, yeah. Yeah?
Could you go back to slide 14, please? So on the y-axis, you have standardized RMSE. Is that the predicted, is that the root, that's root mean squared?
Correct.
That's an indication of predictive power?
Yes.
So why is the predictive power highest at the beginning? It would seem to me, just help me interpret this violates my intuition.
It's not predictive power. It's more of a measure of accuracy of the model.
So it's more accurate early?
No, so it's the error. So the error goes down.
Oh, the error.
Yeah,
okay.
Root mean squared error, yeah.
That makes more sense.
Yeah. Karen?
I have a question. So how much information the teacher can get? Of course, it's very good that to know this particular student need help, but what kind of help? Do you have any insights from the model?
Yeah. So if we go back to looking at the actual interface, we see that, man, there we go. Really all the teacher is getting is that they need help, and then this code state. And maybe if you're like a really expert teacher and really understand the kind of task that the students are doing, you might be able to help the student based on their code state, but chances are that's not going to be the case. So the work that we're kind of working on now is instead of making the representation a code state, we're turning it into chunks of code, right? So you can see the presence or absence of certain code chunks, which might be more interpretable because it's a larger grain size. Yeah, it's a good question. Yeah?
Actually, I had a related question. So you're looking at finding peer tutors who are most likely to be able to help based on the common ancestor in the state model. So this suggests to me at least that you have a pretty constrained solution space. How do you deal with fuzziness in those previous states? I mean, if this were a general purpose programming problem, it seems to me you'd have state explosion and you couldn't determine that very easily. So how are you dealing with that?
Yeah, so that's a good question too. And we do, even, this is a fairly, it's an open-ended environment, but it's a fairly constrained task. So our network is very large and very kind of sparse. So one of the things that we're doing now to kind of reduce the complexity of that graph is by reducing the complexity of the state into the presence or absence of code chunks, which we have some preliminary results that's drastically going to improve the coverage of the graph. I think the broader question that you have is in a less constrained programming environment, which is more common in upper level courses, how would this work? And I think that's an open question. And I think it's a big question in this space.
Yeah. Well, there's some people working on this problem. And then, and the other thing, the underlying assumption here is that people who have encountered those states in the past are most likely to then be able to help people who have encountered, because they've seen their way through. So that's an interesting assumption to challenge, I think, in future work.
Yeah.
It sounds reasonable at face value.
Yeah, but it might be the case that, certain students are, just like teachers are better than others.
Yeah.
Yeah.
So there's just a couple of quick comments I'll make in the peer helping world. I didn't see in your future work whether you're going to turn it into an experiment, but presuming that you are, there's a propensity of how much somebody's willing to help that you might want to consider adding into the formula of choosing a helper, and part of that can be having the one smart student who's going to help everybody as an example, or even worse, the one prototypically dumb student who's run into all of these problems, solved them on their own, and thus gained the knowledge and matches very closely this historical parse tree, now has to help everybody in the class. There's also a benefit to helping, so you learn through helping. It doesn't seem like it's necessarily captured here, although you're not measuring cognitive outcomes, you're measuring skills or actual output. So just a couple of thoughts in this sort of peer helping. Like, this is very interesting work and an interesting approach, but as you bring it towards an experimentation, those are some of the things you might want to consider how you'll handle. Because I think it could really dramatically change how strong of an effect you see.
Yeah. I have not seen work like this that's about efficiency, but I have seen work on peer tutoring that's about, like the learning by teaching kind of literature. Yeah. So yeah, definitely a good point.
Okay, is it time for questions? So I have a question. In regards of the usage of the system, well, one question is if you have shown that to a teacher, the dashboard that you had in the end. And the other related question is if you are envisioning any possible dramatic effect on your algorithm, or with all the assumptions that you set that can break the system, the ideal function of the system once you roll it out in the classroom, like assuming that the teacher is going to use it or misuse it in different ways. Do you have any ideas for future work? Yeah,
so your first question was, well, I'll answer your second question first because that's fresh in my head. So I think the question is, will a real world implementation have enough violations of those assumptions to render the model different? And I think that's a big concern. I think most of those violations are about instructor behavior. So one of the uses of this tool, I think that may remain more constant in the classroom, is the peer tutoring. You could imagine, once you've been deemed a peer tutor, you have a little pop-up that says, "Go help Johnny Smith," and I think if you're a student and you're done, then you're more likely to do that than maybe a teacher is likely to be running back to the computer and helping who the model says to help. But yeah, it's a good question. In your first question,
If any teacher has give you
Oh.
feedback about it.
yeah, so we have 2 teachers on our team that we got a little bit of input on, but I think we definitely need a bigger user study. Yeah.
So
Yeah.
in that sense, I think that it would be interesting to know how they were approaching initially the students, how they were trying to cover the potential needs of the people that were doing the different assignments,
Hmm.
and whether there is a difference
Right.
in the way that now they can approach them. So is it helpful for them, or if they are super under pressure because they are not able to reach all the students in
Right.
in the room?
Yeah, it's suddenly you're aware of all the help that needs to happen, and yeah, I think that's I don't know what you would call it, the stress from having all of this information. Yeah, I think that's a concern as well.
Any last burning question?
I have a question. Sometimes teachers do pair programming
Mhm.
with students. Do you think that this might help kind of put pairs together?
Yeah, I think that's another good use case. So there's a couple ways that you can pair students together, depending on what kind of outcome you'd like. So if you have a low-performing student, you might pair them with a high-performing student to raise the low-performing student up. You can also pair on similarity if you want to reinforce a concept, or you could pair on difference to foster diversity. So yeah, I think this kind of the common ancestor approach would be help more for the first two, but yeah, I think there's a lot of different avenues you could explore.
Good. Okay. Well, let's give Nick another round of applause.